So yeah, welcome everyone. I'm going to tell you about whole systems mapping. And just to give you a little background on me, so I'm a professor at Dartmouth now in the engineering department. My background is in green product design and green buildings. So I was out in industry for 15 years, then went back to UC Berkeley for my PhD. I've done LCAs on buildings and 3D printers and consumer electronics and furniture and apparel. And when I was in industry, did some consulting and teaching or training of people at different companies as well. And one thing that I noticed is that there's a lot of resistance to using LCA in companies, even though it's generally thought of as the most credible and rigorous form of measuring environmental impacts. But a lot of companies feel like it's a lot of work, and because it's a lot of work, it's expensive. You know, if you're going to hire it out and not build up your own expertise within the company, and sometimes there's not a clear return because you do all this analysis and you show the boss, and maybe the boss doesn't do anything about it. And so a lot of companies end up using it just for reporting, which happens at the end of the design process, whereas all the important decision making for sustainability of a product or of a service tends to happen closer to the beginning of the design process. In fact, a lot of it happens before design even begins, when the business managers are deciding on what business models to use. Things like planned obsolescence, they determine a lot of design decisions before design even begins. And of course, that's not the way it is everywhere, but generally speaking, a lot of companies see LCA as a gatekeeper or barrier to creativity rather than a source for ideas. You know, it's part of compliance, not part of creativity and coming up with new exciting ideas and innovation and stuff like that. The sorts of things that gets design teams really jazzed. And so this design method is a way of pulling LCA into that early stage design process. But I do warn you, though, that in order to integrate LCA into the early stage design process, where people do find it more engaging and more of a design tool, you have to be comfortable with large uncertainties, and you're not going to have the level of precision that you do for quote unquote proper LCAs, where you are doing an environmental product declaration or something like that. So this sort of LCA will not be okay for reporting, but it can be very useful for guiding basic decision making in the early stages. And I'm actually going to show you a website. So I have a bunch of free materials on this. You know, you don't need me to come to your company and train your design team in this stuff. I mean, you can, but it's meant to be freely available and out there. So I have an academic publication describing it, but what is more useful for most of you, I think, is that I have a bunch of training materials on the VentureWell website. So they're a nonprofit that encourages entrepreneurship in engineering students. And if you go to their main website, venturewell.org, and you go to the Ideas and Impact menu and Tools for Design and Sustainability, then you will get this whole site full of green design tutorials on all kinds of things. So whole system mapping is the first one, but there's also things on measuring sustainability. So in fact, you can get tutorials on how to do LCA if you're looking to train other people in your company and just get them familiar with it, or cradle-to-cradle certification or EPEAT certification, greener materials choice, reducing energy use and designing for lifetime, etc. So I'm not going to spend a lot of time plugging this, but just be aware this is all freely available material that you can recommend to design teams to help them accomplish the sorts of goals that you suggest for them as an LCA practitioner. And this whole system mapping that we're talking about in this webinar here is all described on this page. I'm going to start out by showing you a video of it, and then I'll look at the exercise and examples that we have that are, again, freely available. So just to start out, this video is going to just take about 6 minutes, and it gives you the rough idea of what this design method is and how it works.
We're going to start by looking at the two most important global principles of sustainable design: whole systems and life cycle thinking. Here's the challenge. Assume you're designing, say, a clothes dryer. You want to make one that's more sustainable without driving costs way up or performance way down. How would you do it? Well, you could let your imagination just run wild and jump in anywhere. But how would you know when you have a good answer before you even know what problem you're really trying to solve? Which approaches should you go with? And how will you make the tough decisions when two strategies conflict? Before you start jumping to conclusions and fixating on any final design solutions, the first step is to more deeply define the problem by looking at the whole system. So let's expand our thinking from the dryer to the larger process of clothes getting dirty, being washed, and being dried. It looks something like this. Now look at the system even more broadly. A marketing person might be able to tell you about how customers actually use their dryers. A manufacturing expert might point out obvious production limitations you'll need to work around. Getting other perspectives early on is always helpful. These kinds of insights help you understand and bound the problem. Now that you see the system, it's time to zero in on how you want to improve it by identifying the biggest impacts and minimizing them. To optimize for environmental performance, you need to consider impacts through the entire life cycle of your product or service. We'll keep our example simple by looking at only the hardware in the system. The washer and dryer impact the environment through their manufacturing, distribution, use, and disposal. At each one of these stages, there may be greenhouse gas emissions, water pollution, air pollution, toxins, or other environmental impacts. Your analysis should measure these impacts to the best of your ability. The most thorough way to do this is called life cycle assessment. You may want to compare your results against some benchmark. In our case, you'll find that reducing the energy use during the life of the dryer offers the most opportunity for improvement, more than raw material use, waste, or any other factors. The important thing at this stage is to realize where the environmental impacts are coming from and quantify them in some way so you know your priorities and can set metrics around them. That way, you can make the case for your environmental goals and fit them in with other project requirements. Okay. Using systems and life cycle thinking, we've narrowed down our challenge from build a more sustainable clothes dryer to use less energy to dry clothes. Now that we've defined the problem, how do we solve it? You might jump into the obvious solution of making the dryer's heating system more efficient. But you're likely to find that heating systems are already quite efficient, and the incremental gains you can make by re-engineering them dry up pretty quickly. Instead of making small improvements to one part of the clothes drying process, let's look for solutions by looking again at the whole system. Notice that the washing machine supplies the wet clothes to the dryer. The wetter the clothes are, the more energy they take to dry, right? Now we can ask new questions like, might we save energy by delivering the clothes to the dryer in a less wet condition? Well, a washing machine already shares in the drying process by spinning the clothes to a damp state with centrifugal force. And here's a chance to innovate. A washing machine with a more effective spin cycle might use slightly more energy, but lets the dryer save a ton more. It turns out that the solution for a more sustainable dryer is a slightly more energy-intensive washing machine. This is just one strategy. By brainstorming, you might come up with a whole slew of other ones. Approaching the problem with a blank slate can help lead you to more drastic innovations, like eliminating the dryer altogether from the system in favor of a next-generation clothesline. Or creating fabrics that need to be cleaned less often. Your broad thinking at the beginning makes seeing these solutions possible. As you start thinking of potential solutions in the context of the whole system, you'll begin to see the relationships between them, and one idea is likely to lead to the next. This is the kind of thinking that's leading to the biggest gains in sustainability everywhere. For tips to guide your brainstorming and help with this design process, look to folks like Amory Lovins and the Rocky Mountain Institute for inspiration. They've developed a whole set of useful principles for radical resource efficiency called the Factor 10 engineering principles. Once you've got a lot of solutions, how do you choose between them? Well, you should go back to the goals you set when thinking about the life cycle impacts of the design and assess each option. Some of these options will obviously be better than others, so you can throw a bunch away quickly. But what about the best few choices that are left? When you compare all your possible strategies against the same criteria of cost, performance, environmental, and social impact, you can make an intelligent decision about what the best solutions are. Once you've chosen a solution to develop, you'll begin solving all kinds of technical engineering problems. Autodesk tools like Inventor and Algor can help you do simulations and analysis to optimize your design throughout the process. For example, spinning the washer faster may require a different material or may create the need for vibration suppression, which brings up new costs and impacts. This time we focused on energy use because that was by far the biggest impact of the dryer. But you may want to repeat this again and focus on the next highest design priority, which in your case might be materials or durability. We covered that pretty fast, and no design process is ever this linear. But every time you run through this process, you're going to innovate. It opens your eyes to the bigger picture and helps you attack the most important problem. Then it breaks you out of your normal boxes to find super creative new ideas and helps make sure you pick the best ones to improve the sustainability of your product. This is how you get the most far-reaching innovation, helping you design products that are better for their users and for the world.
Okay, so that is the design method in a nutshell. And again, this is freely available on the VentureWell website, but I'm going to take you through it in more detail here. And I'm going to show you a set of PowerPoint slides, but you can also find the full list of activities right here on the website with some illustrations as well. There's more in the slideshow that I'll show you, but you can also get this stuff here on the website as well if you want to do this activity with coworkers of yours on design teams or engineering teams. So, okay, let's get the slides. Yeah, so as it said in the video, you start off by looking at not just the product itself in isolation, but you want to look at the whole system. And I have a particular definition for what's helpful here in the whole system. So there is the product itself, and in order to look at that, you want to look at the bill of materials of the product. And this is a difference between a normal detailed LCA, you know, like a proper LCA, versus the kind of LCA that you might whip together as part of this design process. Here, you don't need the entire bill of materials masses and manufacturing methods and transportation sourcing and all that kind of stuff down to every single nut and bolt of the product. You certainly can do that if you have that data available, but if you're just using this as an early stage design tool, you can sketch things in by just looking at what the main sub-assemblies are of the product. So for a refrigerator, obviously it's going to be the body of the refrigerator, so the steel skin and the polyurethane insulation on the inside. You'll have some copper or other metal for the cooling coils and heat exchanger, and you'll have the compressor that drives the cooling cycle and a valve. And so those are the main highlights of the bill of materials, and that's probably all the detail that you need for a very rough early stage design. And you might include, like, if there's electronics in the fridge, obviously that's going to have a big impact, so you should include that. But again, just going for the highlights. And then you draw the rest of the map. And so you've got that whole bill of materials in the middle, and you've got the energy use of the refrigerator up here. And then down, starting at the lower left, you have the life cycle of the fridge. So raw material extraction, some transportation, manufacturing, more transportation to retail. And then at the lower right-hand corner, you've got the end of life, which I've just depicted as landfill. And then in the middle here, you have the actual use of the refrigerator. So the reason that it's got pictures of it with the door open and with a carrot there is because that is how a user interacts with the fridge. That's what you do with the refrigerator. And so you've got the person here getting their carrot out of the fridge to eat. And so that user interaction is important for the whole system of the product as well. And then the last thing is what the product is always used with, because that can sometimes lead to another product that actually has a much higher environmental impact, so that maybe, like in the video, the point is not to optimize the sustainability of the washing machine. Maybe it is to reduce the dryer's energy use, because that is what will make a bigger difference in the whole system. And so in this case of a refrigerator, instead of clothing being the product that's used with it, it's food. And so we also have the life cycle of food in there as well. You don't necessarily have to have that, but it can be a helpful thing. And for instance, if the product were, let's see, if you were redesigning the seats in a car, then the parts of the seats would be in the center, and the user sitting in the seat would be the use, but then the rest of the car would be the product that's used with the system. And so once you've got all these components here, you also want to show how they're connected. In this case, we've got these little arrows going through them to show the flow of time of how these things are used. But you don't have to use the flow of time as your connections. You could have logical connections instead. You could break out the bill of materials into subcomponents and have those connected by what is a subcomponent of what. So the goal here is to have a lot of flexibility in how this is done, because designers, particularly in the early stages, they want to have a lot of flexibility in how they think about things. And so that's the generation of your whole system map. And part of that is honestly just to get everyone on the team on the same page about what problems you're even trying to solve and what you're looking at and what you're not looking at. And so getting yourself as a sustainability expert, the LCA person, into that conversation early in the design process can sometimes be half the battle. If you can just help the design team make this system map and throw in little tidbits of what things they should consider when they're looking at the whole system, then that by itself could be a real win for you, even if the design team doesn't choose to do any of the rest of the design method. Okay, but the second step is where LCA really comes in. First, you prioritize, you find out what your objectives are by doing LCA. And you can set boundaries on what you will and won't include. This may or may not be, so when people are generating ideas later, they may or may not use the same set of boundaries, but this is the set of boundaries that you would use to quantify the environmental impacts, to do your LCA. And so you would tell them, okay, for your refrigerator, this is what the energy impacts look like. It's by far the majority is energy use, but then materials manufacturing is notable, and then pretty much don't worry about transport and end of life. It's mostly about materials. And so this is where you can have different levels of precision in LCAs come in. So most of the time, companies are not inventing a brand new kind of product completely from scratch, right? They're doing version 6.7 of a product that's been out there a long time, or they're doing a variation on a whole platform of products. Maybe Apple is coming out with a new iPhone, but they already have 3 other models of iPhone, and they've been doing this for 10 or 12 years. So in those cases, you can just recycle an LCA from previous versions that are relevant. And maybe if it's a really innovative product, it will sort of split between categories. Like when tablets first came out, they were kind of between a phone and a laptop. And so maybe you take an existing LCA of a laptop and an existing LCA of a phone, and you present both of them. Or like in this case, I'm presenting 4 LCAs because I teach classes where people will have a wide variety of different kinds of products they're working on. And so I'll say to them, if you're doing a big electrical appliance, use this as your guide. If you're doing small electronics, use this as your guide. Often washed apparel, use this as your guide. And if you're doing furniture or other things, use this as your guide. But obviously, these are wildly different recommendations here. They're wildly different hotspots environmentally. And so if you have a company that is developing a variation on a product that already has many other variations, it probably won't look like this. It'll probably look like all of the graphs are almost exactly the same, but have slight variations. And that's the ideal situation, because then you can have your nice high precision LCA, and you can make really precise recommendations based on that. But if you don't have that, then what you can do is you can help the design team whip together a quick and dirty LCA where you're looking at the main impacts from the main components. And, again, you take them through what the main parts of the bill of materials are for that particular product. But anyway, so you do an LCA for them, and then they take that and they put that as part of their priorities. It won't be the only priority. It's obviously never going to be the only priority because the company needs to make money. And presumably they will want the product or service to be good for the users as well. So maybe user convenience of some form will be another priority of theirs. But it's important for them to write out all of these priorities, because that is what sets up the brainstorm. Whenever you're brainstorming, you need to be brainstorming answers to a particular question. So in this case, the question would be, how do we reduce total energy use of a fridge without compromising convenience or price? And so that is the problem definition. That's what you're trying to come up with ideas for. So then you go to the next stage of actually brainstorming those solutions. And I don't know how many of you have design training, but the general way that brainstorms go, these are informal rules for brainstorming, that there are no such thing as bad ideas, so defer judgment. Any idea is okay, basically just because even if 99% of your ideas are useless, people tend to feel like they're getting shut down when people say no to their ideas. So even though lots of the ideas will be stupid, that's okay. But instead of telling your coworker, no, that's a dumb idea, that will never work, instead, the way to do that is to build on the ideas of others. And so if you think their idea is stupid, think of some other version of the idea that would be less stupid or that would actually be good. See if you can turn their idea around. And being visual is good, just going for lots of ideas, but still staying on topic, staying focused on what the question is you're trying to answer. How can we improve the energy efficiency of a refrigerator without compromising user experience or price? And encourage wild ideas. So then the difference between a normal brainstorm and a brainstorm doing whole system mapping is that in whole system mapping, you actually brainstorm on the system map. And you'll notice that this is not the entire system map, this is a subset of it. It's because I'm just looking at the part that we decided were within the boundaries. And like I said a minute ago, these are the boundaries for redesign. They may not be the boundaries for your LCA. Your LCA might include things like the impacts of growing the food, or in the video, we're looking at the washer, but the LCA included the dryer impacts as well. But now that we're brainstorming, we're just looking at the part of the system that we can change, that we're going to redesign. And when you brainstorm on the system map, you can see where you have ideas and where you don't have ideas. And so part of the advantage is that this gives you a more thorough brainstorm, because you can make sure you have X number of ideas for every part of the system, rather than just getting stuck in one area. This is a classic thing with brainstorming and other creativity, is people just get stuck on one particular thing, and they'll have 20 ideas for that, but they'll, like in this case, you'll see that there's 6 ideas for how the structure of the refrigerator is, but there are no ideas for what to do at end of life. There's no ideas for manufacturing, or no material choice ideas. And so that means you need to keep brainstorming. And so here there are more ideas for the structure, but we've got one for manufacturing. Here there are more ideas. Now we've finally got a lot of ideas for energy. We had one idea, before, right here, solar PV, but that was just one idea. So now we've got 5 ideas, and we've got ideas for different materials now, and we've got new ideas for what to do at end of life. So again, this is just a way of trying to make your brainstorm more thorough, so that you can actually make design teams more creative with this rather than less creative. We're not acting as a gatekeeper, we're acting as an ideation tool. And then the second reason that brainstorming on the system map is valuable is because you can intentionally work to eliminate parts of the system, either physical components or steps in the process. So here, up at the top, you'll see, well, actually, let me start on the left-hand side. So this idea, growing food inside the refrigerator. Yeah, that may seem crazy and ridiculous, but it is actually a thing that people sometimes do. I mean, kombucha is grown in, maybe not a refrigerator. Yeah, sometimes a refrigerator, sometimes just your cupboard. Yogurt is sometimes grown at home. So it's not unrealistic, but that eliminates an entire portion of the system map. It eliminates the whole food supply chain. And then over at the right-hand side, no door, but to dispensing food as a liquid. That's kind of a silly idea. It does exist, though, on college campuses for beer fridges. And what that does is that saves energy in the refrigerator by never letting all the cool air escape when you open up the door. But the really radical ideas in this are up at the top. So salting food, canning food, pickling food, etc. Those eliminate all of the hardware of the refrigerator. So those are much more radical ideas than just changing the insulation of a fridge, or changing how big the front door is, or things like that. And so the goal is that whole system mapping gives you both more thorough brainstorms and more radical brainstorms, because you're trying to come up with something for every part of the system, and you're trying to eliminate parts of the system. And then LCA comes back in again in the last step, where you use the priorities that you set in step 2 to decide on what solutions you're going to go with. And this is using LCA in the more traditional gatekeeper sort of fashion. But because it's early in the design process, you'll have very high uncertainty LCAs. So you might have the design team choose their 6 favorite options, and then you can do a rough LCA on all of those. And again, if this is variations on a product that the company has been making for 10 years or something, you might actually be able to do pretty reasonable LCAs in terms of the precision that you can get on them. But if it's a brand new product that's very different from how the company normally does things, then you might have larger uncertainties. And this is the important thing to communicate with your design team, is that you really can't call the difference between these things with lots of uncertainty because they will want to. Anyone anytime sees a graph, they will automatically think that this bar here, option C, is higher than option B, kind of no matter what the error bars say. And so actually one thing that I often do when I'm presenting LCA results to clients or having my students do it is represent uncertainty by blurred graphs, so that they visually can't make that mistake of ignoring the error bars. You literally just can't tell whether option A or option D is higher impact in this situation. But you can tell that option B is definitely the lowest impact. And so, translating this back into the sort of cartoon of the video, this lets you eliminate some possibilities and helps the design team move forward with some. And one thing that I'll do to help people balance their LCA results or the environmental priorities with their other business priorities, in this case, we talked about user convenience and price as their other 2 design priorities. You can use a decision matrix where you weigh each of these priorities that you have. So maybe LCA is your top priority, and so it gets a weight of 5. And maybe user convenience is also a top priority. Maybe it's as important as LCA, so it also gets a 5. But maybe price is not as important, and so maybe you can weigh that as a 3. And then you'll take each of these new ideas that you came up with in your brainstorm, or the top 3 or 4 or 5 or 6 or whatever, and you score them. You say, okay, this one had a mediocre LCA score, but this one had the best LCA score, so it gets a 5, whereas this one gets a 3. And this idea, its user convenience was terrible, but its price was okay, and maybe there's some other priority, and etc. And so you just assign values from 1 to 5 as just very rough values here, and then the total score is determined by how you scored your first priority times the weight of that priority, so 3 times 5, 15, plus the score for this category times the weight of that category. So 1 times 5 is 5, so 15 plus 5 is 20. And you just keep going. So you multiply this by this, and then you just add it all up at the bottom, and you find, oh, ta-da, idea number 3 is the top rated idea. And so that may decide your final force going forward, or you may decide, even though this was the highest scoring one, that's not really the design that we like. And so I think that means that we need to reevaluate what our priorities are, change these multipliers until they do represent what you really care about. And so that is basically it for the whole system mapping design process. And as it said again in the video, this can be an iterative process where you do it multiple times at multiple stages. But again, the process is you start out by setting the problem definition or problem boundaries by looking at the whole system map. And again, this is if the design team does nothing other than just create the whole system map with you helping them to build that, that can create insights all by itself about what they should be thinking about in their design process. But ideally, you then do an LCA or at least sketch out an LCA for them to find the big environmental hotspots. And then they brainstorm solutions using the whole system map so they have more thorough ideas and more radical ideas. And then you bring back LCA to help them choose between the ideas that they had. And that is mostly it. And again, this is on the VentureWell website, and it's got step-by-step instructions here. It has little time estimates for how long these things should take you. It's got some links to other tools. It's got it has an Excel file you can download to do a decision matrix, and it has examples of what people have done in the past as well. So if we click through here, you can see what some student groups of mine have done. So here is actually a redesign of a refrigerator that some students did, and this is how they drew their system map, and they came up with lots of ideas, set their priorities. These are the LCAs that they did of their top, whatever, 8 or 10 favorite ideas that they came up with. And yeah, they did Tracy millipoints impacts, and they also did CO2 equivalents. And they have the decision matrix and descriptions of what the different ideas were. The other example, is also a refrigerator. Their system map looks very different. Like I said, it's a flexible way of doing things. And here are their LCA results. And and this is their drawing of their final favorite design idea. And then they had, more information on it.